Okay, now we're going to attempt a problem where one of the eigenvalues is going to be 0. So I'm going to give this system of linear equations with constant coefficients in matrix form. So the matrix A is going to be the matrix -6, 2, 6, -2. Okay, and also so that we can get a solution without coefficients or anything like that, and I'm going to give an initial condition as well. I'm going to have the solution y at 0 be equal to the vector 0, 4. Okay, so we are going to try to find a solution to this system of equations. And the first thing we do is we make sure that we can find the eigenvalues. And of course, we find the eigenvalues by solving the determinant of the matrix A minus lambda times the identity matrix. We solve that equal to 0. So I find the determinant of A minus lambda I, so that's going to be -6 minus lambda times -2 minus lambda minus 12. Minus 6 times 2 is 12. Okay, I need to solve that equal to 0, so first I'm going to rearrange everything, and once I group everything, I get lambda squared plus 8 lambda, and there's no constant term, and factoring, I get lambda times lambda plus 8. So I need this to be equal to 0 to find my eigenvalues. So the first eigenvalue, let's call it lambda 1, is going to be 0. And the second eigenvalue, we'll call it lambda 2, is going to be -8. So those are my eigenvalues. Now I need to find eigenvectors. For lambda 1 equaling 0, I need to solve this system to find the eigenvector. -6x plus 2y equals 0, and 6x minus 2y equals 0. Okay, it's equal to 0, not some multiple of x, because the eigenvalue here is 0. So 0 times x is 0. 0 times y is 0. That's why we have that there. And if you look at this for a moment, maybe you can see clearly that 1, 3 is going to be an eigenvector. Associated to this eigenvalue 0. So that's one eigenvector. Now let's look at lambda 2. The system we need to solve there is -6x plus 2y is equal to -8x, and 6x minus 2y is equal to -8. Why? Because -8 is the eigenvalue. And then solving this, skipping a little bit here, an eigenvector for this one is going to be -1, 1. And remember, when you're finding the eigenvectors, you can always just use one of the equations. You can look at that first equation and say, oh, I'll let x be -1 because that gets rid of all the negative signs. And then you see that y has to be 2 to make everything work out, or y has to be 1 to make everything work out. And you just put it there. So there's our eigenvectors. So now I'm ready to write my general solution. It's going to be equal to some constant, depending on the initial conditions, times the first solution, which is going to be e to the I, or e to the 0 times t, times the eigenvector, 1, 3. And then we're going to add to that some constant k2 times e to the -8t times the eigenvector for this one, -1, 1. Okay, so there's our general solution. And of course, we can simplify this. Note here that the first term is a constant term. It doesn't change over time. That's because an eigenvalue of 0 means that there are non-trivial equilibrium solutions. In particular, x equals 1, y equals 3 is one of those solutions. So the only part that depends on time here is this part that I'm writing down right now, k2 times e to the negative 8t times the vector minus 1, 1. Now note, with our initial condition up here of 0, 4, we would want to find out what k1 and k2 are. But if you note, if you add these two eigenvectors together, you get exactly the initial condition. Negative 1 plus 1 is 0, 3 plus 1 is 4. So our specific solution is going to be the vector 1, 3 plus e to the negative 8t times the vector minus 1, 1. Okay, so there's our specific solution. Now what I'm going to do is start on a new screen and try to draw the phase plot for the solutions that we have here. So let me get rid of this. Oops. And I want a black background because I think that works out a little better. There we go. So recall we have lambda 1 to be equal to 0 with associated vector that goes along with it 1, 3. And we have lambda 2 being negative 8. And the associated vector that goes along with that one is minus 1, 1. Okay, so let me draw a phase plot here. Oops, let's attempt to do that a little bit better. Okay, there's our x and y axis. This is our x values, and this is our y values. And first thing we note is that the lambda 1 being equal to 0, those are equilibrium solutions, and we have a vector 1, 3. So here's 1, here's 1, 2, 3. This is about the vector 1, 3 that I'm going to draw here. And along this line, the solutions are constant. So if your solution starts anywhere along this line, it does not change over time. This is an entire line of equilibrium solutions. Usually, with these, if we have a non-singular matrix, we only have the equilibrium solution of 0, 0. But this has equilibrium solution of x equals 1, y equals 3, or x equals 2, y equals 6, or x equals minus 1, y equals negative 3. Anything on this line stays on this line over time. Now, our initial condition is 0, 4, so we're starting right here. And you recall our solution that we had was 1, 3 plus e to the negative 8t times the vector negative 1, 1. So this solution starts here, and as time goes by, the e to the negative 8t part takes less and less of a role, and we converge towards the point 1, 3, which is right here. So what we're doing is we're going in this direction, along this line, over time. And in fact, all solutions will flow towards this line here, no matter where we start. If we start over here, we flow towards this line, like this, over time. And note that the slope of this line, the slope of the line with the constant solutions, is 3, because that is equal to 3 divided by 1. And all of these lines here, this line and this line, all of these other lines for the other solutions, these lines that go towards the equilibrium solutions have slope equal to negative 1, which is equal to the y value 1 divided by the x value negative 3 in this vector here. Okay? So all the solutions, no matter where you start anywhere in the xy plane, and you get quickly pulled towards one of the equilibrium solutions along a line of slope negative 1.